Hello, this is going to be a fairly short unit on interpreting the learning rate in stochastic gradient descent as temperature, and also understanding the relationship between the batch size and the temperature of the SGD, and the relationship between the batch size and the learning rate. So let's first think about temperature. So we just showed in the last unit that we want to take the learning rate towards zero. We want to reduce the learning rate during training. And the classical convergence theorem says that if we do that at an appropriate schedule, there's a theorem that says in infinite time we'll reach a stationary setting of the parameters, a kind of local optimum. So let's think about the learning rate as temperature. So the idea is at a large learning rate, we're taking bigger steps in parameter space. And these big steps in parameter space will take us away from an optimal solution, even if we land there. And the bigger the steps we take, the more random this motion is. And if we think of it as a stochastic process, it's going to have some stationary distribution over the possible states, and that stationary distribution is going to have some loss. And the hotter we run, meaning the larger the learning rate, the higher that average loss of the stationary distribution is going to be. So as we reduce the temperature, as we make the learning rate smaller, we expect the average loss to come down. And what we see in practice is learning curves like this. So this is from the original ResNet paper. What we're seeing, let's look first at this solid, big, bold red line. This is ResNet 34. This is validation error. And what's happening is we're running at an initial learning rate, then we cut the learning rate in half. And we cut the learning rate in half, even after it's sort of converged at this learning rate, it drops. And then it converges at that learning rate. This is sort of reaching a stationary distribution. Then we cut the learning rate in half again, and it drops again to a new sort of stationary distribution, a new value of the loss. So just to explain some of the details in this, we have two sizes of the ResNet. This is ResNet 18. I think I might have misspoken. This is ResNet 34. This is validation. This is training loss. It's weird that the training loss is higher than the validation loss. Sometimes the validation set just happens to be easier. It just tends to be a smaller step. Anyway, the point here is that a typical training protocol is to keep reducing the learning rate by a factor of 2 for a couple steps. And when you do that, the average loss comes down. And I want to think of this as a kind of energy related to a kind of temperature, where the temperature is the learning rate. Okay, batch size. So the standard way of formulating mini batching is to take an average over a batch. This is the batch has size capital B, and we're going to take the loss gradient at each batch element and average them over the batch. Then we define this update to be the learning rate times the average over the batch of the gradient. Now, we're averaging gradients when we do this. If we average gradients, we're getting a more reliable estimate of the gradient because we're taking an average of a sample. So it's going to be better. It's going to be less noisy than any one sample. So what happens is this G hat becomes less noisy as the batch gets larger. And that means that the temperature, the amount of noise in the SGD will go down as the batch goes up. So this can be a problem. I mean, suppose you train your model carefully, and in particular, you learn what sequence of learning rates works well. And what sequence of learning rates works well, I would argue, is going to be largely determined by the sequence of temperatures, right? The sequence of loss values that you get. Now, if somebody gives you more hardware, and the rule of thumb is to use a batch as large as your hardware supports. If somebody gives you more hardware and you double the mini batch, suddenly that schedule of temperatures is affected by the batch size. Things get colder. And if it's important to run hot for a while, to sort of, in a simulated annealing sense, to sort of jump around in the phase space. When you double the batch size, suddenly you might be doing something inappropriate if you use the same learning rates that you used before. So what we want to understand is the relationship between the batch size and the learning rate, and sort of correct for this, such that if you know the sequence of temperatures you want to run at, you can run at that sequence of temperatures when you double the batch size. So what I want to do is think about batch size 1. So up here at the top, this equation is batch size 1. So we're just going to look at one loss gradient. We're going to do an update every time we look at one loss gradient. Now, if I use batch size 1, but I run for capital B steps, okay, so we're looking at capital B steps, so it's like a batch, but we're running batch size 1. So what that means is that the parameters are being updated as we visit every instance. So the parameters are changing now as we go through these B elements. We're using different parameters. So it's not exactly the same algorithm as batching with B elements, because when you batch with B elements, you're using the same model parameters at each batch element. However, if you assume that our model parameters are changing slowly, then this sequence of model parameter values is going to be very close to each other. So it's very close to using the same model parameter at each one of those, but that's exactly the batch update, right? So this update at batch size 1 is, it's now summing over these gradients, and summing over these gradients is different from averaging the gradients. So batch size 1 will sum over them, whereas batch size B will average them. And that changes the effective learning rate. So I want to take sort of batch size 1 as defining the temperature associated with the learning rate. So I can take batch size B, and at batch size B, I'm going to get the same temperature if I multiply the average gradient by a batch size 1 learning rate, and then multiply that by B to undo the effect of averaging. So the idea is that this update, where we write the learning rate always as the batch size times a batch size 1 learning rate, what this means is that the temperature you're going to run at is determined by this batch size 1 learning rate, independent of the batch size. So now you can play with the batch size and accommodate and prevent a change in temperature when you change the batch size. And this is closely related to a major event in deep learning practice. So this is a paper that appeared in 2017 that realized or demonstrated empirically that you could run at very large batch sizes. And if you're in industry, you've got a ton of computers, you can run on a lot of GPUs in parallel. And they showed that you could train ImageNet models in hours rather than weeks by making the batch size extremely large. But when you did that, when you made the batch size extremely large, you wanted to scale the learning rate by the batch size. And this is exactly making the temperature insensitive to the batch size. Okay, so that's my short unit on temperature and batch size. Next, we're going to do temperature and momentum. Thank you.